You are welcome to Physics 101 class, General Physics 1. In this session, we will be talking about physical quantities. After this session, you should be able to familiarize yourself with the learning outcome of this particular session. When you have studied this session, you should be able to, 1, explain the concepts and applications of physical quantities, discuss the types of physical quantities, mention the dimensional and dimensionless quantities, state applications of dimensions, and you should be able to identify scalar and vector quantities. Definition of physical quantities. The properties of physical things that are measurable are what are referred to as physical quantities. They are properties that can be measured, numbered, and represented in units. Physical quantities include length, e.g., the length of a truck; temperature, e.g., the hotness or coldness of a room; time, how long it takes to run to the office, or time between one event and the other; mass, e.g., the mass of a bucket of water, mass of stone; luminous intensity, the amount of light shining from a light source, etc. Types of physical quantities. There are 2 types of physical quantities. We have fundamental quantities and derived quantities. Fundamental quantities are the basic physical quantities used in measuring physical phenomena, from which all other physical quantities are gotten. Fundamental quantities possess fundamental units. Derived quantities are physical quantities that are gotten from one or more fundamental quantities. Derived quantities are composed of multiples or ratios of one type or more fundamental quantities. The table on the screen represents the fundamental quantities and their respective SI units. Mass is represented by N, capital N. The SI unit is kg, while the name is kilogram. Length, capital L. The SI unit is small l, and the name is meter. Time, capital T. The SI unit is small x, which is named seconds. Temperature, we can use capital T, you can use K. The capital T represents 0 degrees Celsius, degree Celsius. Then Kelvin, degree Celsius or Kelvin. Electric current, capital I, and is named ampere. Luminous intensity is measured in candela, while the amount of substance is measured in mole. The derived quantities and their respective units are as follows. Area, the symbol is A. The derivative is S squared. The SI unit is meter squared. Meter squared, N raised to power 2. Volume is L cube, that is cubic meter or meter cube. Density is represented by rho, that is mass over volume. The derivative is capital M over L cube. The SI unit is kilogram. L is represented by kilogram, while the L is represented by meter. So L cube is represented by meter cube, kilogram per meter cube. Velocity can be represented by U or V. U represents initial velocity, V represents final velocity. The derivative is displacement over time. It's measured in meter per second. Meter per second. Acceleration is represented by small a, and that is velocity over time. The unit is meter per second square. Meter per second square. Force is represented by capital F. The derivative is FL over T square. That is FA. FA, mass times acceleration. And mass is measured in kilogram, acceleration unit is meter per second. So that is why we have kilogram meter per second square. Kilogram meter per second square. Work done is represented by W, and the derivative is ml square over T square, and is joule kilogram meters per second square. Dimension. Dimension in physics is an expression of the units and characters of a derived quantity in relation to fundamental quantity. There are two groups of quantities when classified according to dimensions. These are dimensional quantities, dimensionless quantities. Dimensional quantities are quantities whose measurement depend and are composed of fundamental units. The fundamental unit being mass, length, and time. They are represented by capital M, capital L, and capital T. Dimensionless quantities are physical quantities whose measurement and units do not depend on the fundamental quantities, and units and thus their dimensions can't be derived since they are independent of the fundamental quantity. Applications of dimension. Dimensional analysis. This is a process of verifying the equation between two or more different physical quantities so that both sides of the equation are of equal dimension. We have an example. We may decide to verify equation of motion. The first equation of motion, which is given as v equal to u plus 80, and see if the right hand side is equal to the dimension of the left hand side. Under standard condition, the right hand side dimension must be equal to the left hand side. As you can see in the equation, final velocity equal to initial velocity plus acceleration times time. And from the final velocity, the unit is meter per second. The initial velocity, the unit is also meter per second. So by the time we perform dimensional analysis on the right hand side and the left hand side, we will observe that both units on the left and the right are the same. Dimensioning is also used to verify the correctness of equation of particular physical phenomenon. Supposing a student is asked to solve some problems. From the dimensioning analysis, you will be able to know whether you are on the right path to the right answer, because the unit, by the time you verify the unit using dimensioning, you will observe that the unit will be accurately the same as the quantity that you are verifying. Physical quantities are also classified based on their magnitude and direction. These are scalar quantities. Scalar quantities are physical quantities that possess only magnitude, we mean size or amount, and no direction. Vector quantities are physical quantities that possess magnitude and direction. Thank you for listening.